Good morning, everybody. We're just going to finish off our little note here on the lab you're going to do today. There should be stopwatches stuck to the front of the desk magnetically. You can use your iPhone or whatever cell phone you have stopwatch as well. And I think there's a bag of tennis balls and maybe one softball, either on the desk or my desk or the front desk or somewhere around there. You guys have seen them. It's what we've used in the lab before. So once we're done this, you guys can go outside. You go to the tennis courts, throw the ball as high as you can up in the air. You may want to stretch your arm first. I'm old. I hurt myself yesterday, but you're young. You could be okay. Throw the ball as high as you can. Have somebody time it from the time that you release it till the time that you catch it, or perhaps it's hit the ground. It's up to you. Throw it a few times. Take your best time. I don't need an average. I don't need all of the results recorded. The only observation that you're going to make in this is going to be the time it takes for the ball to go up and down, and then if you get that far, which you should, come back inside. There is a scale plugged in on my desk. You'll need to weigh the ball that you threw. It's important you weigh the ball that you threw. Okay, so we'll finish off what we started now. How high can I throw the ball straight up? What is the initial velocity of the throw? So we came up with something similar to this. It may still be on the board. Stickman here throws the ball straight up, goes as high as it can, it stops for a brief second and comes all the way back down. And we decided that that was the time we were going to take because it's way too hard to tell when the exact moment is that it stops. It's easier to know when it comes back down and we catch it because we're standing right there. So that will be our delta t. And because that's our delta t, we decided that we couldn't rename anything. Delta d has to be up and down because that's the distance it will cover in that amount of time. And so those are our delta d and delta t. But we all agreed after some discussion that halftime at exactly 1/2 that time is exactly the point when the ball stops way up in the air, which would be d1/2, the displacement of the distance in halftime, which would be the maximum height that the ball reaches, which is what we're trying to find. And so we decided that these red times, these red variables, correspond to what we're trying to find, which is the highest height. We then decided that in our kinematics equation we wanted to use delta d equals v final times delta t minus 1/2 at squared, which is really good, except we said that if those delta d's and delta t's we used, it would not give us the maximum height. It would give us the height to go up and down because that's what it is. So if we want to actually find out what the max height is, what the red arrow is, we need to use the variables that correspond to the red. We need red delta d, which is not delta d at all. It's actually delta d max. So you're going to have to use that new variable here. V final is the final velocity right here at this point because it corresponds to the d max. And if we use d and v for that point, we also need to use t for that point. Now the reason that a didn't get changed into red and we have to redo it is because it's gravity. Gravity is the acceleration. It's the only thing working on it. We will ignore wind resistance, the friction of the ball between the air. We're going to ignore that because it's pretty low when you're throwing a tennis ball or a baseball or something. Well, baseball's not so much, but those yellow balls that may be in that bag are designed to reduce wind resistance. So we can assume that that's just gravity. We'll ignore wind resistance. So that's the same whether we do up and down or just up, which is gravity from the earth. But the delta t, oops, I forgot to change this to color. That will be the same one. We have to use the red ones, which would be the half time. So once we did that, we figured that we know that the v final at the top here is 0, so that goes away, and we get delta d equals negative half at squared, where delta d and t are actually half d and half time. So we have to do that little quick calculation. Once we did that, we decided that, well, we need to figure out what the speed is. Now we could do this with kinematics, but because this is the energy unit, we have a test pretty soon, I wanted to use energy for that. So we look at the law of conservation of energy. Says that total energy is conserved no matter where in this flight, up or down, no matter what point we choose, the total energy is the same. All that happens is it transfers. It transfers from kinetic into gravitational potential. So right down here, if we have the ball here, just as it leaves our hand, it's basically all velocity due to, or all energy due to the velocities. It's half mv squared. Now it does have some gravitational potential right at the beginning because it is about a meter above the ground or so. So I'm okay if you make the assumption that that is height of 1 meter roughly that we're throwing it from, 1.5 meters maybe depending on how tall you are, or if you wanted to just call that 0 for the sake of simplicity in this lab, that's okay too. So the total energy initially, right when it leaves, would be the kinetic energy, 1/2 mv squared, and its gravitational potential, which is either going to be h of 0 or 1 or 1.5, depending on what you want to call that. That total amount of energy initially is all it has at any point through this. And so we say that the E initial equals 1/2 mv squared plus a mgh, so all the energy it has, is the total energy it has. Which means that if I look at any point all the way up here, including this very special point at the top, at the max height, it's also equal to the kinetic energy that it has and the gravitational potential that it has. Now in this case, I don't have any kinetic energy because right there, the V is 0. Right there, I know the height because I calculated in my last thing. I know that that's the max height. Now I need an M, so you're going to have to use a scale. But I also know that at the max height, no matter what happens here, the ratio is the same, and that also equals my E total, right? Because anywhere throughout, it all equals. And so what I find out here when I get my little trusty bear with me 1 minute. Click, click, click. What happens is I get 1/2 mv squared plus mgh equals 1/2 mv squared plus mgh, which is confusing except when we realize that this is initial and this is at max height. And so no matter where they are, it equals the exact same thing, just the variables change. So I know my initials. I don't know my initial speed, but I do know the mass. I do know my initial mass, I do know gravity, and I do know the initial height. So I can solve for this except for the V. Over here, I know that V is 0 because it's max height. I know the mass, I know gravity, I know the height there. So if this side equals that side, the only thing missing is my initial velocity, and I can solve for it by setting those equal to each other. And that's how you're going to calculate the maximum velocity or the initial velocity of your ball. And just to check, once you've got that initial velocity, we can go back to our kinematics equations. You know the maximum height. You know the time it takes to get you to the maximum height. You know the acceleration due to gravity. So you can plug all those numbers into our other kinematics equation and solve for VI, which should equal your VI that you calculated using energy. And so that's a good check to have. So once you've done all of that, here are a couple of discussion questions. So you will just you've got your purpose, you've got your little system diagram procedure from yesterday. You'll take your time and your mass, your calculations. That's all can be part of discussion as well. So do all of your calculations. Make sure it's all complete. All of your pluses, your minuses. These are vectors. You need directions. You need to answer these 2 questions here and write me a conclusion. How high did it go? What was your initial velocity? That'll be your lab for today. So that should take you most of the period. If you get done early, then you want to excuse me, check out stuff for studying for your quiz and make any questions that you have for me because I'll be back tomorrow and we'll get ready for that. Some point today, check the internet because I will post some sample questions from the 4C book for practice for your test. And guys from the 4U, you guys just got to do your you've got to do those questions that I gave you the other day, the little mini quiz, which a lot of you are probably done, and we'll take that up tomorrow, get momentum started. It's been a while.